Yeah, so my training's in physics and math, and I've been studying now for a few years sort of the information content of neural networks. So how complex are neural networks really, and how does this complexity drive their generalization properties? Cool. And then recently I've been linking these ideas about the information theoretic complexity of neural networks to the geometry of the loss landscape. So I want to tell you about some of my latest results. I actually have some new stuff from the last week or two. So you will see some very sort of jaggedy looking plots from not a lot of seeds being run on some of these newest experiments. But I think you'll agree that the results are interesting, and yeah, I'm excited to tell you about it and talk about it after. Okay, so our fundamental question is, why do neural networks generalize? Why do they generalize? What causes that? So we have sort of the classical theory of the bias variance trade-off, right? So what the classical statistical theory tells us is that as we make our models more complex, we expect the generalization error to go down and then up again. So what should you imagine? On the left side here, our models are not complex enough to fit the data. So this is something like maybe we have a linear model and we have some very complex data, something that actually wants like a 1,000-dimensional parametric model, and it's simply not fitting the data. So what's dominating the generalization error here is actually just the training error is very high. Okay. Over on the right side, you have the opposite effect. So here, our model is far too complex. So what you might imagine here is maybe is kind of the opposite of the previous case, where it's something like it's actually just linear data with a little bit of noise, but now I'm fitting something like a 100-degree polynomial to it, and I'm just wildly overfitting. So even though the training error is maybe minimized, maybe it's 0, the model complexity is far too high, and so we don't generalize. What we really want is for our model complexity to match the complexity of the data set. That's what we want, and that's when we generalize the best. And this intuitive notion is typically formalized with these generalization bounds. Sorry, this just says complexity. So this is obviously an informal statement. We'll look at some very specific examples of these, but in general, they say the generalization error is bounded by the training error plus the model complexity. So we're going to be looking at this model complexity term a lot and seeing how it controls generalization. And if you have any questions along the way, please ask me. I'd prefer if it's more informal, but does that make sense so far? Good. Okay. So this is the classical picture we have in our heads. And today we're told that neural networks break all of this. So there's this sort of famous observation, I think originally from OpenAI, although simultaneously observed by a lot of different people in deep learning, where as we make the neural networks bigger, we see that the training loss just monotonically decreases. And the test error goes down as we expect, and then up again as we expect. So this is what we expect from the previous theory. But then something strange happens. After a certain critical size, making the model bigger, which we're supposed to believe is the same thing as making the model more complex, actually makes the generalization error improve monotonically forever. So this is supposed to be, oh my gosh, deep learning is breaking the classical theory. Is that really possible? No, I mean, that's a theorem. So I think kind of maybe the only possible explanation, and I think that I've now proved this, and this is sort of the first announcement of this result, is that the size of the network is not the same thing as the complexity of the network. So there's a decoupling of complexity and size. So that's double descent. So it's this empirical phenomenon that we would like to explain with a theory. So let's get into complexity. What is complexity? There's actually so many different possible definitions of complexity. So the one that was sort of classically studied most, like this theory is sort of laid out decades ago, is this function class expressivity. So this basically says there's a lot of possible functions that can be represented. So if I have n outputs and m inputs, I have n to the m. I have exponentially many different functions on those sets. And these complexity measures just measure how many of those functions can my network possibly represent. So of those exponentially many functions, how many can the network represent? So as you make the networks bigger, obviously they can represent more and more functions. So these quantities tend to grow as you make the networks bigger, just monotonically. So these can't possibly explain what's going on, because as we're making the networks bigger, they're generalizing better. So some relevant notion of complexity must must actually be going down. Okay. So this is sort of what mathematicians like to prove theorems about. On the other hand, we have these geometric quantities. These are the ones that machine learning practitioners actually use in practice. So this is going to be something like the norm of the parameters. Or another popular one is the curvature of the loss landscape. So this is called the sharpness. Okay, those are the geometric quantities. And then we have sort of the ones based in information theory. These are going to be things like description length. So these are things like the Shannon coding rate. So how many symbols do I need to represent my information? Or if you combine Shannon with computability theory, you get the Kolmogorov complexity. So this is the shortest description when I have access to a Turing machine. Okay, so these are all very different from each other. And one of the things I'd like to do for you today is sort of tie these geometric quantities the practitioners tend to actually use to the information theoretic ones, so that we can see what exactly is the relationship between these two. And we're just going to ignore these for the rest of it.
Branton, I can ask you a question.
Yeah.
Where would piece of
That would probably be like parameter count, I would say. Yeah, that's a good question. It could go kind of in either of these things. So if I think of the parameter count, and then it has associated like information per parameter. So typically I think of like a FP32 parameter. Then the naive description length of the model might be the information per parameter times the number of parameters. Yeah. So that would set kind of an upper bound on the complexity of the models, right? If I couldn't compress the weights at all, if they're completely incompressible, then their description length would be proportional to the number of parameters. But what we're going to find is that the parameters are actually very compressible. And so you can get much tighter complexity bounds.
Does that mean about compressing particular values rather than all of the weights? How are you compressing them in some way?
No, I mean, it probably would be joints. Yeah, probably would be joints. Yeah, good question. Okay. I really wish this was not here. Cool. So what I want to talk about first is these geometric quantities, these geometric complexity measures that the machine learning practitioners actually use. So typically, if you talk to people in the industry, when they want to measure a model overfitting or something, they're going to look at their parameter norm growing really large, or they're going to look at the curvature of the loss landscape going very sharp. But there's a kind of a massive mathematical problem with these geometric quantities. And that is, we can reparameterize our function. Okay, so our network parameters represent some function, but that map from parameters to functions is not injective. And there's lots of symmetries in the network parameterization such that I can reparameterize my network and get the same function. Okay, so there are these reparameterizations that leave the function invariant. So a very famous one is if I just have a two-layer MLP, a two-layer Rayleigh network, if I scale one of the layer's weights up by alpha, and then I scale the next layer's weights by alpha inverse, for any alpha, okay, so any alpha, that leaves the function invariant, but it changes the parameters arbitrarily. Okay, so this is the problem. If I'm looking at curvature, okay, so the curvature here, I can actually change it arbitrarily by doing this reparameterization. And these geometric quantities are not invariant under reparameterization. So in some sense, they can't possibly be the full explanation for generalization, because generalization is a property of the function, not of the parameters. Is that clear? Any questions on this reparameterization issue? That it can't possibly be the full explanation?
Well, the generalization is a property of a function, but the particular function that you got when you learned is not necessarily a property of the function, it's also a property of the parameterization.
The particular function you got is not a property of the function? That's what you just said.
Yeah, the choice of function is not just based on the function, because you learn in parameter space.
Right.
So.
Oh, I agree. Yeah. So learning.
Yeah.
Yes. Yeah. absolutely agreed with you 100%. So the dynamics of learning and the regularizer and all of these specific things probably choose specific length scales, right? So even though there are reparameterization symmetries, the learning process is not reparameterization invariant.
Exactly.
Yeah, so I agree. So that breaks the symmetry and chooses some preferred length scales. Of so of the parameters. Right. So I just gave an example where I can scale up all of the parameters in one layer by alpha, and then scale down the next layer's parameters by alpha inverse.
Yes.
And I can make alpha anything. I can make it 10 million. Yeah.
Positive.
Yes. Yes. That's right. So
that's what you mean by length scale.
That's what I mean by length scale. Yeah. So the reparameterization symmetry, of course, is more general than just rescaling symmetry. So it's any diffeomorphism. So I can apply some diffeomorphism to the parameter space and leave the function invariant.
Yeah.
And then that's going to change these geometric quantities arbitrarily, but the function is not going to change. Okay. Yeah.
What do you mean by not changing? It's very clear that those are some symmetry functions.
So this is the loss landscape. It's not the function.
Cool.
Yeah. So the geometry of the loss landscape is going to change, but the function is not changed. And the generalization is a property of the function.
Actually, saying that you've got a loss landscape model and you optimize that, and all three of those have some kind of permutation variance.
This isn't about permutation invariance, but let me get back to this. Let me go on. Okay. So that's kind of the big problem with the geometric measures of complexity. So let's review a little bit the information theoretic notions. Okay, I've annoyed many people with this GIF many times, but anyway, this is just a nice thing I found on Twitter many years ago, where if you plot the JPEG file size of this image over time, what you find is that it rises, it comes to a peak, and then it falls. And so JPEG, of course, is a lossy compression method, and we're going to see how lossy compression methods can be applied to neural networks to understand their intrinsic complexity. Okay, so what are the basics of information theory? So the foundational result in the field is Shannon's source coding theorem, which just says if I have n random variables, so maybe n is now something like my parameter count, where they're drawn from some distribution x, then I can compress them into no more. I can compress them down to n times the entropy of the distribution, number of bits. So that gives me a coding length. So that says the description length of those n variables is somehow proportional to the entropy of the distribution. So this is identifying the limit of compression, the entropy of the distribution. Okay. Then, of course, Kolmogorov extended this idea. So now he wants to consider computability at the same time as information content. So you can notice in Shannon's definition, we require an entropy. So that means we have to have a random variable. So we can't really talk about the description length of computable objects like pi or something like that. They don't have a Shannon entropy. They're not random at all. They're deterministic objects. So the Kolmogorov complexity identifies the description length of x, k of x, with the length of the shortest program, such that when I run that program on a computer, I print out x. Okay, so it's saying the shortest possible description of x is its complexity. Okay. So those are the information theoretic ideas around complexity, but how do these relate to generalization? So that's kind of the big question for us if we want to study these neural networks and understand why they generalize. What is the relationship between complexity and generalization? So there are these generalization bounds. I'm not going to really explain how one arrives at them. These have been known for decades, but I'm going to tell you what they look like so that you have a feeling for it. So it says, for any prior distribution over hypotheses P, and any posterior distribution over hypotheses Q, then with probability at least 1 minus delta, this holds. Okay, so we're going to make delta small, so the probability is high. What does this say? So R of Q, this is the generalization error of our posterior Q. Okay, so this is, I'm going to put a distribution over parameters Q, and then R of Q measures the generalization. Our hat of Q, this is going to be my empirical risk. This is the error on the training data. You can just think of this as the training error. What is this controlled by? We don't really care about this. It's definitely controlled by the number of samples I see. But the complexity term here is the KL divergence between Q and P. Okay, so the complexity term here is the KL divergence. So it's really worth just reviewing what is KL divergence. Why is it interpreted as a complexity measure? Okay, and here's the definition of KL divergence. It's the relative entropy between the two distributions. And the KL reports the excess information needed to code things from Q when my codebook is optimized for P. It's basically telling me how much additional information is there in Q above P. How much additional information is there in Q? One of the nice properties of the KL divergence is that it's reparameterization invariant. This is sort of a trivial, this is a one-liner. Q and P are just some distributions. And if I do a reparameterization, that reparameterization applies to both Q and P, and that reparameterization just falls out in the integral. Okay. So it doesn't have that problem that the geometric complexity notions have. It's reparameterization invariant. Okay. Is that clear? Are there any questions on the KL divergence? Just want to review the basics, yeah.
This is
yeah, so this is going to be a distribution over my parameters.
yeah, like you would get if you were doing Bayesian inference on the parameter space or something, right?
You could get a distribution that way, but you're actually free to choose any Q. So I can put any distribution on Q.
Okay. Okay.
This is then the training error under Q. So it's like the average risk under all of the parameters in Q weighted by their probability under Q.
Yep.
So this is the training error. This is the test error.
Yep.
And then this is that complexity.
And why does it depend on the? How does maybe R depend on the prior? Because it seems like I could. Another way to make this boundary.
You have to choose the prior before you see the data. So yeah, you could put the prior just exactly on your weights that you found, right? And then the complexity would be 0, but that would be cheating. So the prior does have to be placed before you see the samples. Okay. One of the trade-offs, which we're going to talk about this later, is no, we'll just talk about it later. Okay. Yeah, so this is what I wanted to say. If your prior is not good, you choose a bad prior, you won't be able to simultaneously minimize the empirical risk and the complexity. So we're going to be looking for a distribution Q that's going to simultaneously minimize the complexity and the training risk. But if you have a bad prior, then you're just never going to be able to do that.
Minimizing the bound, right? Because this is just a bound.
Yeah, that's right.
Okay.
Okay. I think I'm going to just skip that. Yeah. Okay. So here's another strange generalization result from deep learning in the last few years. So this is with a large transformer. You can imagine a few 100,000 parameters. And the task is to learn to do some modular arithmetic. So it's very, very simple task, like x plus y mod p. So this is the training accuracy. You can see after just over 100 steps, it's perfectly fitting the training data. Perfectly fitting the training data, 100% accuracy. And the test accuracy stays low for very, very long time. It's on log scale. Thousands and thousands and thousands of steps later, suddenly it generalizes perfectly. So what's causing this? So in my previous work, I did some studies of the compressibility of the parameters of the neural networks. And so what you find is when they're memorizing this training data, when they get 100% training accuracy and 0% test accuracy, the compressibility, the compressed file size of the network parameters is sort of maximized. And as they generalize, the file size falls drastically. So this is a nice empirical result. And we can theoretically understand this, but we didn't have enough control of the theory. And so I think that's what we have now. So I want to tell you about a new idea. Okay. So you asked about the posterior. You said earlier, is this something we might get from like Bayesian inference? So we're free to choose the posterior however we want. And what we want is to simultaneously minimize that complexity term and the training risk. Okay. So one idea people have had is to actually use the geometry of the local loss landscape to encode a posterior. So what is the idea? The idea is if I'm at a flat minimum in the loss landscape, I can code my parameters very coarsely. I can choose a code book such that I code these like very, very coarsely. And then, right, when I snap to that code, I'm only going to induce a little bit of error. Whereas if I did that same very coarse coding on these sharp minima, I would induce a lot of extra training error. Okay, so we're going to construct a posterior based off of the local curvature of the loss landscape. And that information is going to be encoded in the Hessian. It's clear why, right? This is just a matrix of second derivatives. So this is the curvature of the loss landscape. Okay. So we're going to finely code in sharp dimensions, and we're going to coarsely code in flat dimensions. Okay, so let's get a little more specific. That's all been very, very hand-wavy, very high level. So let's get very specific. So we're going to put a very uninformative prior over our parameters, just a Gaussian centered at 0, with some length scale variance sigma squared. I'm going to choose some length scale sigma squared. And here's the posterior we're going to do. We're going to center it at the weights that we arrived at from training. So it's going to be centered at our SGD weights theta. And we're going to put some covariance over it. And this is, I'm just claiming if this is true, this is the optimal covariance for this prior. So this is based off of Hessian. And then it reduces to the prior. And the Hessian eigenvalues are small. Okay. So if you have this prior and this posterior, this is the KL divergence. So this is your complexity term. So let's take a look at that. Did you say? Yeah. So when my Hessian eigenvalues are small, yeah. So when these go to 0, you can see that the posterior falls back to the prior. Yeah. And when the Hessian eigenvalues are large, when it's sharp, then the covariance becomes very narrow there. Does that make sense? Yeah, thanks. Cool. Okay, so let's look at that KL divergence term. So this is our complexity term. Okay, so given that prior and given that posterior, this is the complexity of the network. And there's something very interesting. Look, theta squared, L2 norm, L2 norm of the parameters, and log determinant of sigma. That is the curvature. It's the log curvature. So this is reparameterization invariant. It doesn't suffer that problem that the geometric quantities have, but those geometric quantities that everyone's using pop out. Okay? This is why people empirically observe these things correlating, because as you said, the learning process picks out some length scale. We don't know what that length scale is, some sigma squared, right? We don't know what it is, but it picks some length scale. And then when you've chosen that length scale, indeed, the L2 norm and the curvature do control the complexity. Is that clear? Any questions about that idea? So this is why people are seeing these things correlate. It really does control the complexity.
This is still a stronger claim because you're talking, oh, this is about a bound.
Mm-hmm. Yeah.
So
that's right. Sorry.
What you're really saying is what you really can say is they control the bound.
That's right. Yeah. Okay. Okay. So at least we can control this generalization bound. To me, that's sort of the acid test of a good complexity measure. Like, does it actually give you a non-vacuous generalization bound? Okay. So people are sort of very hand-wavy about complexity, like, oh, this is a complexity measure, this is a complexity, and you sort of make like philosophical arguments for such things. But to me, the test of like, is this a real complexity measure? Is like, do you have a non-vacuous generalization bound? Does it actually control the generalization of your network?
So it's just something.
Meaning the bound is tighter than random performance, or the bound actually tracks the test error.
The bound actually tracks the test error.
Yeah.
So
Yeah.
I guess that's what's coming next.
Indeed. Okay. I'm going to come back to that actually. So let's skip to what's coming next. So this is a very new result. So apologies if the plot is not very pretty. So here's that grokking example where the training error, I don't plot training error here, but the training error quickly falls to 0. And then the test error stays very high for a long time. And then it suddenly generalizes. So here I'm plotting that generalization bound with that KL divergence complexity term. And you can see it's actually tracking what's going on here. So I think this is the first non-vacuous generalization bound for grokking.
Put these on the same plot.
Yes, it's true. my yeah. Yeah.
Actually stay above.
Yes. But that's a good sanity check. Okay. So another thing that you can see from this construction is there's actually a trade-off between complexity and risk, right? So if we make our posterior Q bigger, the coding rate goes down. It becomes closer to the prior. So the effective complexity of that model goes down as we make Q larger. But also as we make Q larger, the empirical risk goes up because now we're including sort of weights that are very far away from the mean. And so there's going to be a trade-off between the complexity and the risk. Does that make sense? So I want to now define the complexity at a certain level of distortion. So this is going to be the minimum information, the minimum complexity of our weights, the min KL divergence, such that the empirical risk under Q, the difference between the empirical risk under Q and the risk of the mean parameters, the ones you actually got by SGB, that is bounded by epsilon. So that's going to be our distortion threshold. So this is a rate distortion trade-off. So this is the coding rate of the model, and this is the distortion constraint. We don't want the empirical risk under Q to be different from its mean by more than epsilon. Okay. So now, if we look at, again, apologies, the plot is that it's very new. It's a new result. So this is just showing you double descent is indeed occurring. So on the x-axis, we have model size. So these are all different models trained independently, and they get larger and larger and larger. There's the test error, it goes down and then up and down again. And if you plot this complexity and KL complexity versus the model size, you find what I was expecting to find for a very long time, which is the information in the network is actually maximized at these smaller intermediate sizes. And the largest models that generalize best actually have less information in them. Okay? So just to say again, just to emphasize, the largest models are simpler than the medium-sized models as measured by this KL divergence.
How is this? Is this really fundamentally different from having the complexity bound? Once you have the complexity measure, then you also have this by the, like you were already talking about the prior in terms of like also like you talked about dividing the parameter space up into bigger chunks. So what's actually different here? Or is this just like,
so this isn't plotting a bound, this is just plotting the KL at some level of distortion and showing what that level of allowed distortion is. Okay. I think the next plot will answer your question. Okay. So the problem is at different levels of distortion, you get a different measured level of complexity. And our bounds are not tight enough. And this is why no one saw this effect until now. when you find the complexity that optimizes a particular pack-Bayes bound, the level of distortion that the trade-off between complexity and distortion that the bound ends up selecting is that it pushes the distortion almost to random performance. So it prefers an almost completely random model to optimize the bound because the bound is just not very tight. And so you see when it's monotonically increasing, when the KL is like a monotonic increasing function of the number of parameters, that's when epsilon is very large. You allow a lot of distortion. But as you shrink epsilon, as you say, no, you're not allowed to have large distortion relative to the mean, you find that that rise and fall of complexity appears as you shrink epsilon. Does that make sense? So yeah, no one had seen this effect because if you just optimize the bounds, you don't find it. You actually have to shrink epsilon, the distortion level, underneath what the bound would select, and then you see the rise and fall of complexity. So it's kind of a hint that our bounds are really not even close to tight enough. They're not able to explain.
There are other people that did complexity in different ways. Like you're calling the number that this is plotting like information content or complexity, right?
At a certain level of distortion.
Yeah.
Yeah.
Okay, but like for a given level of distortion, you have a particular complexity measure.
Yes.
Let's say.
Yeah. We have an upper bound on it. There always might be like a more optimal coding scheme that you just don't have. So this is like under your class of posteriors.
Okay. Sure. Yeah. So then I'm wondering, like, because I've seen this kind of curve before when someone plotting some other complexity measure that they use some method to estimate for like a given neural network parameter, and it tracks like double descent in this way.
Really?
Yeah.
Oh, okay. I'd love to see that. Yeah, let's.
For example, Andrew Gordon Wilson has this paper, rethinking parameter counting in deep models, effective dimensionality.
Yeah.
This with the number of the number of effective dimension.
Oh yeah. The effective dimension. Yeah.
Yeah. So it goes like this as well. Another complexity measure.
Yeah.
So I'm wondering.
So this is an improper complexity measure. Yeah. So I mean that one's not reparameterization invariant. I agree that there have been these hints, but that doesn't measure the information content. That just measures the number of active dimensions of the model. Yeah. But it has a scale problem where you have to choose the scale to define what active means. Yeah. Yeah. So in his papers where he actually tries to measure the information content, like in the LLM generalization bounds, when they do the same thing on double descent, they're not able to find this effect. I was talking to Andrew a few weeks ago about this, actually.
Yeah. The other place I have to check is.
Yeah. Yeah. So this is very much inspired by Andrew's effective dimension thing and wanting to make it rigorous. But it has the scale problem. That'll be next. That's next. Thank you. Cool. So as Will pointed out, the KL changes a lot as you change the distortion. So this is our rate distortion. Okay, so we can actually compute the rate distortion curve of the model. If you plot it on a log plot, you find straight line. Seems to be a power law. Most rate distortion curves, like classical, like your data is coming from a finite dimensional manifold, you tend to get a log rate distortion curve. So it tends to be that KL is proportional to the log of the distortion. But here you find power law. Yeah, okay, good. So we find this power law. And if you plot the exponent of the power law lambda against the actual tester, you find that it predicts generalization in these difficult double descent examples very, very well. So this is so far an empirical result. And of course, it inherits the reparameterization invariance from the KL. Yeah, sorry about this. So blue is the training error, just goes down. Red is the tester, down, up, and then down again. And green is this lambda, the summary of the entire rate distortion curve. So this is going to be our scale-free complexity measure goes up and then it goes down. Okay, so that's kind of the new result that I just got in the last 2 weeks. I want to share it with you all. So lambda is somehow summarizing, as I change the allowed distortion level, how much does the coding rate, how much does the complexity of the model change? Okay. We find that it's a power law. We suspect that this controls generalization. And of course, I think sort of the golden prize, which I have not yet achieved, but hopefully soon, is kind of the biggest result in deep learning of the last 5 years is, of course, the scaling laws. So what are the scaling laws? The scaling laws plot the test loss on the y-axis, and you plot these 3 quantities on the x-axis on the log scale. This is the number of steps you take to train your model, so how much compute you set the model. This is the size of the data set. And this is the number of parameters. You find a power law in all 3 of these. So that's kind of what has driven the last 6 years of making computers so big and throwing billions and billions of dollars at these models, is because there was this very regular law that gave people confidence that as they scaled the models up, as they scaled the compute up, things would go well. And I think we're all looking for sort of a theoretical explanation for why is it these power laws, and can we predict these power laws without doing these massive scale experiments? And so I kind of suspect that there's a way into predicting these power laws from this rate distortion curve. So I haven't done that yet, but hopefully soon. Okay, so
This point is just because this is.
no, you can. So this is what I'm like doing this week. So this is a very new result. I found this parallel 1 week ago. But you can get some metric entropy generalization bounds from lambda. So you do like a covering number argument, and you can see that the generalization error becomes a power law in the data set size, where the power is a function of this lambda. So you can get some functional relationship between the lambda I found and power law of something like times. Yeah. So how do you extend it? So here's a fun point. So if you think about it, double descent is sort of the change in generalization error as we change the number of parameters. Grokking is kind of the change in generalization error as we change the number of steps. So I think potentially we can unify, grokking, double descent, and these power laws from this rate distortion perspective. Yeah, well.
This is how this definitely you do have data.
Well, it has to be a function of the data, right? It has to be a remnant of the data. Different data sets have different complexities.
Language, for instance, about vowels.
Yeah. Yeah.
So, can you say, for instance, that this is to do with the models and not the data?
Well, it's going to be some interaction between them for sure. Yeah. So I think one line of theory that has also gotten to the power laws from a different direction is this neural tangent kernel, this NTK stuff, where you take the infinite width limit of the models, and then the scaling law exponent comes from the spectrum of the NTK. And I think it's pretty straightforward to show that the Hessian spectrum is shared between the NTK and the Hessian share spectrum. So I think that's kind of intuitively the link there. Cool. So that's pretty much it. Yeah. So what I'm claiming is this is kind of the first information theoretically rigorous demonstration that the larger models in fact learn simpler hypotheses than the smaller models in double descent. I think we have a nice explanation for grokking in double descent, and I think we have a route into deriving the scaling laws from this rate distortion curve. Yeah, so that's it. Thank you.